Thanks and welcome. And it's a pleasure to me to give a report on my lecture from last summer term. Just in general, this is a course we teach together with a colleague from the technical thermodynamic chair. And we will give it over several years as a combination of an engineer and a mathematician. And at first, I will shortly give you an impression what we do inside that lectures. And as already said, we have students of different engineering courses, and what we do is that we will show them how they can produce their own code with Matlab, and even they have already heard a course in the first semesters in the bachelor studies, they are usually quite far away from programming at all. So the first part we like to do is to repeat and show them some basic features from Octave or Matlab, and this is one of the first sessions we do, but our focus will then go on to solve this stationary heat equation in 1D, which is very powerful. And here we show them as a combination of how to produce matrices from these derivatives and how to formulate this with finite differences, and to show them even the connection between the fundamental theorem of calculus and the solvability strategy and knowledge from systems of linear equations. Finally, we will guide them that they will model the Rankine process, and all these engineers usually know this process very well from other subjects. So the question in general is how to do that. Do that synchronous or asynchronous? And we have run this course already several years, and there we already did some kind of blended learning. So that means that we already used or try to engage them, that they will prepare some topics, and we will discuss about that in the present settings. But for myself, I'm a passionate teacher for in present, and I like to talk to them. And as Peter already mentioned, that he drifts around and talks to the students, I do the same, and I like it very well. And this is a bit difficult to do that online. Inside the course as a general target, we try to engage the students to repeat known concepts, like mathematical concepts, like how to solve a linear equation system and what do you know about the uniqueness of the solution, and what do you know about the modeling of physical processes. What we have done is to move our present session to an online session. This will take part every 2 weeks for 4 hours, and this is a coding session and a discussion session for modeling questions. And what we introduced were a question hour on Tuesday on the week in between, where the students already ask some question from the last session or what they have prepared for the next session. And all the material I have provided via our learning management system based on ILIAS. It's one not very known learning management system compared to Moodle, but this is used in our university, and I'm very satisfied with that. How the lectures runs now. Inside our learning management systems, I have prepared for every session one section, as you see there, or here, this is the 5th section I prepared. And then you see here something like it's called a Clausius Rankine process. And so this is what the students will find, and here's already the first question. We start usually between 20 and 30 students, and we'll end up with the half. So between 10 and 15 students will run this course up to the end, and not all of them need the credit points. The most of them just do it to learn something without need of the credits. And all the course is partitionated in several sessions. So at first we start with fundamentals in Octave or Matlab. Then they have to start with a learning module. It's based on the antiderivatives, what we do there. We will introduce finite differences in first order and even the second order. And as already mentioned, and now they have the connection between the first or second math course, and now they have to rediscover what they have learned already. Then we have seen we have to go a bit slower. That's why the second order differences, we shifted into the third session, and then we tried to solve the static heat transfer. And then we added the transient heat transfer using the ODE functions like ODE 23 or 23S. And then we start with the final project, the Rankine process. And such a learning module looks like that. Here you see a German snapshot of that. You see here the definition of the finite differences first, or for the first order derivative on a grid with equidistant points. And at the end, you see here there are two tasks for them, and they should write down a linear equation system of all this. Or when they start to think about the Clausius-Rankine process, as it's called in Germany or in German, then you see here the process at all, and then you have here some gaps, and they have to model everything, the pump and the vessel and the turbine and the condensator, and then they have to calculate all these data by mathematical models. And here a lot of discussion raise up. The question time looks like that. We will discuss what will happen if you write down the matrices, and then we can talk about the rank of the matrix and how to solve it and what the boundary conditions will do and why they are needed. This is one screenshot from my tablet, or here you see a discussion of the heat transfer problem. This is a heat transfer problem which describes three different things, like the heat distribution, the temperature distribution in the plate over the thickness, or in a cylinder sphere over the thickness, or in a sphere even over the thickness. What you see here, this is a connection to the third class, where the fundamental solution is computed of that model, and even here we have a link back. So at the beginning, we start with classical lectures. The lecturer show something and directly typing inside Octave, sharing the screen, and the students do the same, and they directly can ask their questions. Later, the students will discuss their own code. They will copy them into a common Etherpad, and then I will copy it on my machine, will run it, or they will share their own machine. So what we had this year was a very lively discussion about the modeling of the Rankine process. This was with respect to the highly nonlinear properties of steams and water. And if you skip the third or fourth digit after the dot of the decimal number, then you will get completely different results. And this was a very interesting discussion this year, much more lively than in present. Often I'm only as a keeper of the minute, so I will write down what the students will say. And sometimes it happens in that way that I introduce a problem and I will discuss with them what happens if I do some computations together with them, and they will tell me what I have to write. Or I can add, can remove some mistakes in typesetting. Or here, this is an example. My colleague, Professor Wensing, talked about the problem about the heat transfer into the earth from above, and how to compute some data from a heat pump in his own house. And I just made this small picture to illustrate what he has said. This is what we have used to exchange code. You see here, this is just an example to write down a small function and to make some plotting. And this was our exchange basis for code. The communication usually done with all channels we had. So we used mail or forum. This is what not the most session, but a lot of vocal interaction. And what we have done is, with respect to the small course we have asked each participant what they are doing, which problems they have. And this was quite interesting, since some people gets their question during talking. So this was a quite good idea than screen sharing or coaching via our learning management course, or even debug code online from the together with the students, and to show them what how different approaches could be look like. Or even that they will get an impression how the solution looks like. I sometimes provided some interactive applets. I will show this at the end. What is the students' feedback? The students' feedback is that they were all satisfied. Only 8 people took place, all were very satisfied with the course. They invested partially a huge amount on time. If you see here, this is 8 to 12 hours per week. This is much more than it's addressed. And so they were very satisfied with the motivation of all those lectures, that we answered all the questions, and even that we have repeated some concepts from the bachelor math courses. And so we could combine even the combination of learning modules provided in our learning management system, and then the interactive Zoom meetings. What they missed the fast exchange between two other students to develop a solution together with them. But on the other side, one people wrote that he or she felt less pressure to find a solution if the other are faster. One said, I missed nothing, it was even the same, and we could communicate some facts much more clear. So what was the course general? We started this year with 20 people, ended with about 10. I do not know exactly because as the last things I will get in the next week. Then the official workload is 75 hours for the whole summer term, and this has 14 weeks usually here in Bavaria, in Germany. The assessment, what they have to do is to write a small program package, and that contains the program files, the documentation, including a reference example. And then in the first stage, they have to do a peer review of the documentation of one of the other students. And after that, they will deliver a revised version to me to get my final feedback. I have used a Surface book together with a second monitor and a pencil for the Surface to write on it, and software I have used the GNU Octave on Windows or Matlab. It's as the students liked. I have used both, and the PDF annotator software to write inside the PDF slides, and the learning management system ILIAS, which is called Stut-on at the FAU. It's called something like Study Online. And if I can have a last second, I would like to switch over to a different just this different picture. I have to start it again. So here I have it. Here you see an interactive applet of my of the heat transfer equation, where they can see which results they should expect. You see here you can change the dimension of the space between 1 and 3, and then you see here the sphere. You can change the discretization manually, and even a constant heat source in that interval. So you have an heat inflow or a heat outflow. You can change the interval, in general, even the boundary conditions. And this is based on JavaScript. So what you have seen now was computed online just in time inside the browser. So this is what I like to report you, and I have to say great thanks for your attention. And so if you like to know a bit more about that, please feel free to contact me. Thanks.
Thank you very much for that really interesting talk. Now, Jotham, do we have time for a question?
We've got time for perhaps one quick question.
Okay, so a question I've received. Now, you talked about liking the fact that you were able, pre-COVID, to go around and actually talk to students and see how they're getting on. So do you have practical tips how we can replicate that in an online environment?
I'm not sure I understood everything right, but what I have done is, our university is using Zoom at time, and I had a very small group, and we have directly asked every student directly, what is your work, where you are, what is your state, and then they are talk to us, or they even shared their screen and directly pointed to the problems they have. Answers this your question, or?
Yes, indeed it does, in terms of having to deal with a very small class. Any sort of ideas how we could do that sort of thing with much bigger classes like many of us are teaching?
I'm not sure. So what I would try to engage the people, even to build up our groups inside, for instance, such a learning management system, and that they will discuss there and get the option to share code where they can even type inside directly, like a shared document. This is what we can do with our Etherpad, and maybe even with a or smaller mailing list or forums to divide them into smaller groups so that then they can talk together like offline breakout rooms in Zoom. This is what I would try and what I'm thinking about for my basic lecture in the first math course next winter term.
Okay, thank you. Back to you, Jotham.
Thank you very much, Wigand. Very interesting indeed.